Good day! I'm Dr. T and welcome to my office. So today I'd like to talk a bit about gravity. And when doing so, of course, we're all familiar with gravity, so I want to go a little bit more into the weeds and talk about it in a little bit more detail. But what I don't want to do is jump into a lot of detail. So I'm going to be talking about gravity in terms of Newtonian physics, not our better but far more complicated understanding of gravity that has developed in the 20th century. So things like depressing space-time and changing its shape, I'll leave that for a different video, probably not starring me. So let's jump into gravity. So Newton, of course, is like, hey, things fall down, and extends that to why the planets are in orbit and other things. That gravity goes beyond just this earthly realm and extends out. So he comes up with the equation, the force of gravity. So that's the actual force pushing you down. So that would be your weight. That is going to be a function of the mass of the two bodies interacting. So that would be you and the Earth. Obviously, the latter is a bit bigger than the former in that particular case. Divided by the distance between their centers of mass squared. And that squared is going to make a big difference. Now, a couple of caveats. Obviously, this distance between centers of mass, we're assuming all of the mass is at a point that's at its center of mass. That is an assumption. And it's an okay assumption in many cases. And it's not an okay assumption in some cases. So like if you travel around the Earth, the force of gravity actually varies. And that's because the Earth is not a perfect sphere of uniform density. There are certain parts that are denser and have more mass directly under you than there are of other spots. Not to mention, the Earth isn't flat. Either, flat or smooth flat, either definition, it's not. It's pretty close to the sphere, but definitely not quite. So with that caveat ahead, let's jump in a little bit further. So if we've got this, a couple of implications are here. One, the farther away you go from something center of mass, so say the higher up you get, the less gravity is going to be pulling on you. Now, Earth is big. You need to be, if you want to divide your gravitational pull by, say, a factor of 4, you need to go double the distance. Yeah, Earth orbit ain't double the distance. If you've got a ball of, if like a peach is the Earth, then Earth's orbit is still within the fuzz kind of scenario. So keep in mind, Earth is big. Okay, so now we can imagine an item, and you've done this before. Cats love this. Take item, push it off a table, it falls straight down. Now, if you remember back to vectors, if you take an item and you push it off the table, so it's going this way, and now all of a sudden no table, and it's going this way, the two vectors add together and it falls in an arc. This is fairly straightforward. And for relatively short distances, this works well. By the way, I'm also going to be assuming that there's not an atmosphere, because the atmosphere adds drag, it slows things down, and when I jump into the realm of orbits, you always want to do your orbit high enough up that you don't really have much of an atmosphere. Low Earth orbit still has some atmosphere there, and that's why satellites will eventually fall down. They've got some drag there. But you want to get rid of most of your atmosphere to do this. Okay, so imagine you're up above the atmosphere, and the classic analogy is a cannon. So you got a cannon sitting on a hill, and it shoots a cannonball. So of course the cannonball is going to go whoop. You can change the angle of cannon, but right now we're just going to assume it goes straight. Makes the math a little bit easier. Okay, so we've got the cannonball, and it falls down. But the Earth isn't flat. Let's say we fire the cannonball really, really fast. And actually, if you look at something like a battleship, obviously they're putting an angle to it, but they're shooting far enough that the curvature of the Earth actually matters. And the cannon shell will go farther because the Earth is dropping away. So, you got your cannon, it's up here, it fires the shell, but the Earth is dropping away so that as it drops, there's more distance for it to drop. Okay, so let's get a bigger gun, a faster gun. We're going to fire that cannon shell really, really hard. Eventually, you can conceptually think of it that the cannon shell is traveling far enough that as it's traveling, the Earth is dropping away because the Earth is a sphere, so you're going around the sphere, that the Earth is dropping away at the same rate the cannon shell is dropping. So it doesn't actually go any closer to the Earth, it's falling around the Earth. And this is the core of an orbit. If you've got something going fast enough, then simply its motion, as it's being pulled towards the center of the thing, towards the center of your planet, your Earth, or whatever you're orbiting, you're going to be going horizontally or tangentially to that fast enough that you're going to whip around it, but you're not actually going to collide into it. And thus, you would come right back and go through the breach of the cannon again, assuming the planet you're on wasn't rotating, which of course the Earth is rotating. So, complexities. Okay, we've got the beginnings of an orbit. If I take my whatever, and by the way, turns out cannons are really lousy to do this. That's why we use rockets. They work a lot better for going ludicrously fast. So if you take your satellite and you put it up and you launch it high up, rocket goes straight up to start with. You know, planes go forward and then up. If you, well, hopefully not that. That's a trip. But you're going to have, whereas rockets go, and then eventually they do a weird roll. Usually that's to make the math easier. Turn over on their side and go horizontal. It's interesting to actually launch one, or to look at how they fly. Usually you can just barely start to see the turn because it's so far away you can't see them. And that's the goal, to get the rocket out of the atmosphere. Okay, so we get the rocket. It goes up. It gets out of the atmosphere, or at least out of most of the atmosphere, because the atmosphere goes up really far. It gets out most of the atmosphere. It turns, and it's going to start going sideways. So at this point, it's going to go sideways really quick, and then eventually it's going to run out of fuel, or stop the engines, because usually you're not done yet, even when you're going. Okay, so if you stopped your engines and you had enough energy, enough velocity to go and whip yourself around the Earth, great, you're in orbit. Now that orbit's not permanent, because there's things like drag, so you're still going to hit a little bit of the atmosphere. It's going to slow you down. And then all of a sudden, once you slow down to the point where you don't have enough energy to make it all the way around, eventually you're going to spiral in. You're not going fast enough to meet back up. As you know, the Earth is dropping away, you're getting closer and closer. Okay, so if you're going too slow, you shut your engine off too soon, or eventually you had drag and you're going to start slowing down, then eventually you'll spiral in and hit the ground. Now, imagine you're going a little bit faster, enough that you're able to go, and you're actually not falling as fast as the Earth is turning away from you. Well, in that case, instead of having a nice circular orbit, and pro tip, very few orbits are circular. This is what messed with Copernicus. Instead of having a circular orbit, you're going to have an elliptical orbit. You're going to go, you're going to overshoot, but now you're not going straight tangential to the source of the gravity. You're going a little bit off to the side, so you're going to slow down a bit from gravity, and then you're going to arc, and you're going to start falling back down, and you're going to speed up, and you're going to whip around. You're going to go fast when you're close, and then when you're on the opposite end, you're going to go slower. And this is what we see with planets. This is Kepler's big invention. Kepler realizes planets don't orbit in circles, they orbit in ellipses, and they don't orbit at the same speed. And that's why Copernicus, his models didn't work at all. Kepler's modifies them, makes them work a lot better. Anyways, so now you've got yourself your ellipse. A couple things you can do at this point. One, as you get out here, you can use your engines to speed yourself up a little bit. And what you're going to try and do is you're going to try and reform a circle, but you're going to try and reform a circle farther away. This is called circularizing your orbit. Whenever you're looking at a spacecraft, they're going to fire, probably drop off a stage or two that lowers the mass so they can keep going. And then they'll turn off their engines and they will coast. They'll go into that ellipse, and then a little bit later, they'll burn their engine again, usually about halfway around. They'll burn their engine again, and then that will turn their orbit into a circle because they'll have enough velocity at this point to, instead of being this egg-shaped orbit, to be a round orbit but higher up. The higher you are, the faster you have to go. Okay, now, got a couple other options. Let's say I want to leave my gravity. Sometimes we call this a gravity well, but leave my source of gravity. What I have to do is speed up even more. So now, as I slow down, I never slow down enough to the point where I'm no longer going to fall back. So I have to be fast enough that I overshoot. It's no longer an ellipse. It's still kind of an ellipse, but all of a sudden other gravity sources take off. So if I'm on the Earth and I make my ellipse long enough and I point it kind of moonwards, then as I'm traveling, I'm going to move from the gravitational influence of the Earth to the gravitational influence of the moon, and now I can go in an orbit around the moon. I still have to fire my engines a couple of times, so just to make sure everything works, because I need to vary my speed as I'm traveling. If I'm on the Earth, I just burn really quick. I'm going to leave the Earth's gravity, and I'm going to go and be experiencing the sun's gravity, which is much stronger than the Earth's. Remember, distance matters here. If you look at the moon has only 1/80th the mass, but it has on its surface 1/6 the gravity. Why the discrepancy? Because the moon is smaller. The distance in that equation is much, much littler. Okay, so yeah, we've got our basics. If you're dealing with gravity, obviously the farther away from it, the less of it you feel. By the way, it never goes to zero. You never completely leave the influence of something's gravity. You just become influenced by other things, more so. And then, hey, if we want to go into, say, orbit, what I'm really doing is I'm not trying to go up to a place. If you simply launched straight up, and there's work on a rocket that'll do this, launch straight up, turn off the engines, don't turn sideways, you will fall right back down. And there's a group that's working on setting that up for tours. Pay a bunch of money, get on a rocket, go straight up, look out the window, go ooh ah, fall down, parachute goes, and then they go there. Thank you, have a very nice day. Next kind of scenario. So that's going to happen if you just go up. So up isn't going to cut it. You have to be going up and then lots of speed going sideways. Of course, when you return from orbit, you, of course, seen the pictures, you know, the spacecraft barreling down, the flames coming off the spacecraft. What's happening is you're taking all that energy you put into it, you got to get rid of it. You got to slow down. And you're going to slow down by squishing against the atmosphere. So you use your rockets to slow down a little bit, and then you squish against the atmosphere, and then you either use more rockets or a parachute or a combination to slow it down enough so you can make a nice, gentle touchdown on the ground, assuming that's your goal. But yeah, so welcome to rockets, and see you next time.